So today we'll focus on tutorial sheet 1. So for those who are new to Transcended Institute, what we have to know is that we do have all the videos on our platform. So we have the website where we post our videos for all the NS courses. Okay, so first let's solve this question and then I'm going to show you how you can access the videos. So the first question is a spring that obeys Hooke's law has a spring constant K. Show that the energy stored E in the spring when it has been extended elastically by an amount X is given by W is equal to half Kx squared. So how can we show that work is equal to half Kx squared? This is the basic thing you need to understand under Hooke's law. Okay, so I can say this question is coming from conservation of energy, where we have the elastic potential energy, because elastic potential energy, I believe to say you have done this topic. Elastic potential energy is the same as the work done by that force which you have. Okay, now one thing you have to understand is that if I take you back to semester 1, we do know that work is equal to force times distance. Now if we are talking about the spring, if this happened to be my spring, I'm trying to stretch it. Okay, so at this point this is going to be my equilibrium position. At any equilibrium position, X is always 0. That is very important. We need to know that X is always 0. When X is equal to 0, that is what we call at equilibrium position. The force that is pushing this spring to go in this direction is what we call the applied force. I'll put it here. Now, as you are stretching the spring, there is a force that is pulling the spring back to the original position. That force is what we call the restorant force. Therefore, the restorant force is given by negative Kx. Where is this negative coming from? From the equilibrium position all the way to this point, we have got the distance which we call x. X is the displacement in this case. Now, since the displacement is going in this direction, the restorant force is moving in opposite direction. That is the reason why this formula has got a negative, in case you don't know. So the force which we are interested in is the restorant force. The restorant force is the force that makes the spring to go back to its equilibrium position. That is very, very important. Okay. One thing we have to understand is that when we are doing deformation of solid, you came across this. So this is the force in this direction, which is in Newton, and this is the displacement in meters. You discover to say if we have got the spring which is directed in this manner, I can find the work done covered by the work done by this triangle here. One thing we need to know, guys, here is that if I want to find the work done here, this is x and that is the force in y direction. To find the work done in this case is to find the distance covered at that point. What do I mean? How do you find the distance in this case? What is the distance of the triangle? How do you find the area? Sorry. The area of the triangle is given by half BH. So if you want to find the work done by any force or by any spring which you have, which is I've given you a graph in this case. So to find the work done is the same as finding the area under that curve. In this case, I've given you this curve to be my triangle. Okay, I want to find the area in this case. Okay, B is the x in this case. So I'll replace b with what? Half with x. My h is force in this case, which is the height. It is the force. One thing we need to remember now is that since we are saying that the work done should be equal to the area under the curve, I'll replace A with W. So where there's A here, I'll replace with W. So I'll say A is equal to half. Then I've got the force times X. This force which we're talking about here is the restorant force. So the restorant force, I'll replace this with just Kx. Is that cool? So I'll replace where there is F with Kx. For now, I'm going to ignore the negative. So I'll say the work done will be equal to half. Where there is force, I'll put Kx again times X outside. X and X is going to be X squared. So I'll end up having this. I can clearly see that this is equal to that. Hence shown. Unless you have got a question on how to come up with this formula. Any question? Okay. Now there is another method which I'm going to use, which is and this method you are going to understand it. Yes, you can ask.
Sir, can't see the screen. Can't see like what you're writing.
I believe that should be your network. Anyone who can see the screen again? Or is there anyone who can see the screen? Anyone? Respond. Just respond. You can unmute yourself.
I also can't see the screen.
Same way, if you are unable to see the screen, sir.
Who are able to see the screen? So try to leave the meeting. Try to leave the meeting and rejoin again. Because I've also managed to log in using my phone, but I'm able to see the screen. So that should be your network. Now another method which I can show you on how you can come up with this formula is by using integration. Using integration, I can clearly see that work is equal to force times distance. The distance we're talking about here is the x. So work will be equal to the force times x. I can integrate both sides. What do I mean? If I want to integrate this side, I'm going to integrate this with respect to x. So if I get the integral here, meaning this x is going to change to dx. So it's going to be work will be equal to the integral of f dx, like that. At this point, I can clearly see that f is equal to kx. I will replace f with kx. So work will be equal to the integral of kx dx. So if you know calculus, I'm integrating this with respect to x. What can we see? We can clearly see that work will be equal to k is constant. So k will just be like that. Then x, now x, the power has to increase by 1 divided by itself. So it's going to be x 1 plus 1 divided by 1 plus 1, which is work will be equal to k x squared divided by 2. These 2 which I have here, I can write this as 1 over 2 kx squared. So you can show this using two methods. The first method I've given you and also the second one. But if they are going to give you this question as an assignment, I can recommend the first method which I use and not the second one. because the second method which I've used is for advanced physics, where you talk about calculus. You use calculus to derive this formula. Okay, is that okay? Now, one thing you need to understand, guys, in case you are new to Transcended Institute, I want just to show you something. Okay, so we have got the website. If you go on our website, you just type Transcended Institute, you go to our website, you'll be able to see this. Okay, my network is not stable. I hope you are able to see my screen, so you'll be able to see this. Now, as you can see here, guys, we have got all the courses. We have got math, physics, biology, and chemistry. So I'll first go to math. Okay, in case you want math. So I'll scroll down to set 2. This is for semester 1 for now. So for semester 2, start from calculus, or let me start with complex numbers. So if I go down, I'll be able to see complex numbers here, which has to be just here. So this is complex numbers, as you can see. Now, complex numbers, we've got complex number basics. Then there's also quadratic equation for complex numbers. Then further complex number, De Moivre theorem, polar form, and nth roots. We have got polar form. We have got polar form to rectangular form when you want to convert maybe from polar form to rectangular form. We have got multiplication and division of complex numbers. Then we also have the solutions for tutorial sheet. So we have got this tutorial sheet for complex numbers, as you can see here. This is tutorial sheet. Then if you started calculus already, you can also go to calculus limits. So we have all the videos for limits. Also for differential calculus we have. For integration we have. For differential calculus we also have. I can also show you physics, since we are doing physics right now. Let me just show you physics. Let me just show you physics. Okay, so if I click on physics here, if I go for semester 2, I'll be able to see which starts from vibration and waves. So you can clearly see here that we have got the videos for vibration and wave. We have got the vibration and waves, which is Hooke's law introduction. Then we have got tutorial sheet 1 part 1, tutorial sheet 1 part 2, tutorial sheet 2 part 1. Again, we have all the videos for vibration and wave. Even tutorial sheet 2, the solutions are ready. Tutorial sheet 3, all the way to tutorial sheet 4. Then we also have, like for this one, which is deformation of solid. And then we have got Hooke's law introduction, cash up classes. This video, we solve the past paper questions and also tutorial sheet questions. Then you can go to the second topic, which is sound. We have got intensity, spherical wave, Doppler effect. Yeah, we have all the videos. So once you register with Transcendent Institute, what you're going to do is you learn at your own time. Okay, you just make the timetable. You'll be learning with us, learn the smart way with us. So if you want to register with us, get in touch with one of the admin in the group, or if you don't have any number, I think I can just put it here so that anytime you want to get in touch with us, so you can get in touch with us using this number, +260767 729927. So WhatsApp this number, you'll be able to register with us. So without wasting much of our time, let's go to question 2. So where is our question 2? Our question 2 is here. So the question is, a light spring of an extended length of 14.2 centimeter is suspended vertically from a fixed point as illustrated below. A mass of weight 3.8 Newton is hung from the spring as shown above. The length of the spring is now 16.3 centimeters. An additional force F then extends the spring so that its length becomes 17.8 centimeters. Part 1. Show that the spring constant of a spring is 1.8 Newton.
No, you can make. But yeah, you can make. You can survive.
Okay, so that is part 1. We want to show that the spring constant of the spring is 1.8 Newton meter to the power negative 1, which is the same as Newton per meter. One thing you have to understand here, guys, is that this is always given by a negative kx, and our goal is to find the what? We want to find the spring constant, which is k. How can we find the spring constant? So first thing we have to identify our x. What is our x in this case? So I will start with the first one. Before this force, we know that the original length is 14. So to find the x will be equal to 16.3, which is centimeters, minus 14.2 centimeters. So my x will be equal to, if I get my calculator, I say 16.3 minus 14.2. I'm getting 2.1. So my x is 2.1. One thing we need to understand now is that the force which have been given in this case is 3.8. Okay? So now, in this case, I'm going to ignore the negative. If you want to include the negative, meaning this force has to be negative as well, because k can never be negative. Okay? We are finding the k constant. So the force is 3.8. I'll put 3.8 here. Okay? This should be equal to, I'll say the k I don't know. Now the x is 2.1. Now this is centimeters. The force is in Newton. I'll put it in Newton like that. I can divide both sides by 2.1, even here by 2.1. So now this is in centimeters. So I can clearly see that my k will be equal to, I can cancel these two. This and this can be cancelled. So I'll say I have got Newton on top, and down here I've got centimeters. So 3.8 divided by 2.1. I'm getting 1.809. So 1.809, which is the same as, it's going to be Newton per centimeters. Now we can clearly see that this is in Newton per meter. This was just a mistake. It was supposed to be show that the spring constant of the spring is 1.8 Newton per centimeter. So this is how we are supposed to show that. Unless you have got question before we go to part 2. Any question? Any question? Okay. If you have got question, you can just ask. Okay. So we go to the second part, which is saying, now I'll put my k here, which is 1.8 Newton per centimeter. Now in this case, because I am going to solve part 2, I think it's okay for me to change this k to be now in Newton per meter. So how can I change this? I think if I just divide this by, I'll do this. Okay, let me just go direct to part 2, which is saying For the extension of the spring from the length 16.3 centimeters to a length of 17.6. Okay. For the extension of the spring from the length of 16.3 centimeters to a length of 17.8 centimeters. Part 1. Calculate the change in gravitational potential energy of the mass of the spring. Now, let's understand the question. Gravitational potential energy. There is what we call elastic potential energy. Elastic potential energy is given by half kx squared. Gravitational potential energy, it is the one, gravitational potential energy is the one we are doing in semester 1 under work energy and power, which is mgh. Okay? So we want to find the gravitational potential energy. So we can clearly see that we want to find the gravitational potential energy, and mg we have been given in this case. What is our mg? What is our mg? Who is going to help us? What is our mg in this case? We want to find the gravitational potential energy. Okay, my mg is the force which I have in this case. So if I want, I can find m. That is, if you want, you can find m, which we don't know in this case. You can say the force is 3.8. In this case, this 3.8 is the same as is our g, is our mg. Is that okay? So 3.8 is the same as my mg. So now I need just to find the change in gravitational potential energy. So the change in gravitational potential energy is going to be my initial gravitational potential energy minus the final gravitational potential energy. What does it mean? When I say my initial minus the final, what I mean is this. I'll say the mg times the change in h. The change in h in this case, I can clearly see that this came from 14.2 all the way to 16. That will be my initial. The final now is this 17 minus that. So my x in this case is my h. So I will say my change in h will be equal to h2 minus h1. Now to find h1, in this case h1 is going to be this minus that. Is that okay? Okay, if you're behind, let me know so that I explain. If you're behind, let me know so that I explain. Okay, no one is behind. So now in this case, let me just go direct instead of me wasting time here. I want to find the change in gravitational potential energy. You know, when I was talking about the change, it is the gravitational potential energy final minus the gravitational potential energy initial. Now in this case, I know that I'm just dealing with mgh final minus mgh initial. That's why I say it is the same as just saying my change in gravitational potential energy will be equal to, I can factor out mg, then I'll say h final minus h initial. So which h are we talking about? The h final is this. They are saying that for the extension of the spring from the length of 16 to this. So that is my final. Now I have to convert that to meters. So I'll say 17.8 divided by 100, meaning I'm converting this from centimeters to meters. That is going to be, it's going to give us what? What are we going to have? Those having calculators, what are we going to have? Okay. So if you change that h, I can't get you, sir. What are you saying? It's going to be, your network is tripping. Your network is tripping. I can't get you. It's going to be 0.17. Okay, 17.8. 17.8 divided by 100. Okay, so we are going to have, okay, 0.178, right? So I'll say my first one is going to be 0.178, like that. And my second one, if I convert this 16.3, what are we going to have? Divided by 100, what are we going to have? Those having calculators,
We're going to have, yeah, we're going to have 0.163 meters.
0.163 meters. Okay, let me first ask you this. Are you okay with me using this formula, or maybe you're okay with me using just the final gravitation? We find the final gravitational potential energy and the initial, then we do minus. Which one is okay for you, or just direct?
I think we should just go direct. It's okay.
Direct is okay with you?
Yes.
Okay, so our friend is saying direct is just okay. Anyone who is confused, so that maybe we see how we can help each other? No one is confused, huh? Okay. If no one is confused, now I'll also convert. I have to convert this one. So this is going to be, okay, let me just do this, because I know some people are confused already. So the change in gravitational potential energy to be potential energy final minus potential energy initial. Let's first go ahead and find the initial potential energy to make things simple. Or we start with final. So the final will be mgh. Now final, the h final which we're talking about is this minus that. Now we divide it by 100, so it will be 17.8 minus 14.2. That is going to be 3 point what? 3.6. So 3.6 centimeters, I have to convert this to meters. I'll divide it by 100, which is going to give me 0.036. So I'll say my mg is 3.8, which we have the um the force which you have, the weight force which is there. So I'll do times 0.036, and I'll end up having what? 3.8 times 0.036. 3.8 times 0.036. That is going to give us what? I'm getting 0. Can you confirm 0.1368 as my final? Now to find the initial, I'll use the same method, but this is going to be now mgh now initial. So initial is this minus 14.2. 16.3 minus 14.2. So I'll say 16 point. You have got a question? I'm getting 2.1. I divide this by 100. I divide this by 100. I'll be able to get 0.021. Now I do my initial will be equal to 3.8 times 0.021, like that. So 3.8 times 0.021, I'm getting 0.0798. So I'll say the change in gravitational potential energy will be equal to, the final is 0.1368 minus the initial is 0.0798. So I don't have space this side. I think I just shift it a bit. This should be 9 and then 8. So my change in gravitational potential energy will be equal to 0.1368 minus 0.0798. So I'm getting my answer to be 0.057 joules. So that is my change in gravitational potential energy, unless you have got questions. Can we go to the last part? The last part is saying show that the change in elastic potential energy of the spring is 0.077 joules. One thing we need to know is that the elastic potential energy is given by half kx squared. Now our k should be in Newton per meter. So in this case, let's go ahead and find our k in Newton per meter. So F will be equal to, my F is 3.8 in this case. 3.8 to be equal to, my K I don't know, my X. Now my X I'll use the same one. Last time we say this minus that one, which was 2.1. So in this case 2.1, we have to convert this to meters, which will be 0.021 if not mistaken. So 2.1 divided by 100, 0.21. So I'll say 3.8 is equal to 0.021 k. I divide both sides by 0.21, even here 0.021. These two will cancel. So I'm going to have my k to be equal to 3.8 divided by 0.021. So I'm getting 180.95, which is the same as 181. 181 Newton per meter, like that. Now that I have my k in Newton per meter, I'll put it there. My k to be equal to 181 Newton per meter. Now I can find my change in elastic potential energy. So I'll use the same one. I'll say my change in elastic potential energy will be equal to the elastic potential energy final minus the elastic potential energy initial. So to find the elastic potential energy final will be equal to half k x squared. So which x are we talking about for the initial one? Sorry, for the final one. It's going to be that minus that, which is 17.8 minus 14.2, which is 3.6. 3.6 is in centimeters. We convert it to meters, so it's going to be half. My k is 181. Then my x now, 3.6 is my displacement in centimeters, divided by 100 to get it in. So it will be 0.036. Now you square it. So what will be our elastic potential energy final? So it will be 0.036, I square it, times 181, then times 1 over 2 is the same as 0.5. Those who have got calculators, what are you getting? Okay, I think I'm getting 0. I'm getting 0. I'm getting what? I'm getting 0.117288. Confirm. Is that what you're getting? Those having calculators, please help me. Those having calculators, help me. What are you getting? Okay, so I'm getting 0.
I'm getting 0.117288.
Okay, 7288 joules. So now let's find the initial elastic potential energy, which will be the same as half, and then I have got my k is 181. Then my x now is this minus that. It's the one we had, which was 0.021. Now you square it. Let's see what we're going to have. So 0.5 times 181, then times 0.021, I square it. I'm getting my elastic potential energy to be 0.03991. Confirm. Confirm. Okay, so now I'll
The answers are the same, sir.
okay, thank you. So now I'm going to say the change in elastic potential energy. Remember, our question is show that the elastic potential energy is 0.077. So let's see. The change in elastic potential energy will be equal to the final elastic potential energy is 0.117288 minus the initial elastic potential energy is 0.03991. So if we do minus, what are we going to have? The elastic potential energy will be 0.117288 minus 0.03991. So I'm getting my answer to be 0.0773. But since our answer is in just 3 decimal places, I'll leave it there. So we can clearly see that the change in elastic potential energy is indeed 0.077 joules. And that's the answer we have just come up with here. So the next question is determine the work done by the force F. To find the work done, to determine the work done by the force is just to do this. It's just simple. So the work done by the force, if you have both elastic potential energy and gravitational potential energy, just get the elastic potential energy, the change in elastic potential energy minus the change in gravitational potential energy. That would be the work done by the elastic potential energy. Sorry, the work done by the force. So now we found our change in elastic potential energy to be 0.077 minus. Then we found our change in gravitational potential energy to be 0.057, if not mistaken, like that. So we do minus. So the work done by the force will be equal to 0.077 minus 0.057. I'm getting 0.02 joules. So that is it for this one, unless you have got question. You can ask if you have got questions. Now, for this tutorial sheet, which is, I believe, let me just do this. I think if you have this tutorial sheet, guys, the questions which are remaining here, we have solved this question. We're remaining with question 2. We're remaining with question 2b and also question 3. But if you want to access this, the full tutorial sheet 1, tutorial sheet 2, 3, and 4, what you have to do is just register with us. You'll be able to access this tutorial sheet. As you can see here, the answers are here. I have the answers here. I solved this tutorial sheet. So we have got tutorial sheet 1, part 1, and tutorial sheet 1, part 2. I explained everything. But before you solve this tutorial sheet, you need first to watch this first part, which is vibration and wave, Hooke's law introduction recorded class. This video has got everything for the introduction which you have to know. Okay? And then we also have the videos for waves, like I said. So if you are not yet registered with us, get in touch with me so that you subscribe for these videos, and then you'll be able to watch these videos at your own time. Okay, so this is what I had for you today. Unless you have got questions, then you can ask before we call it a night. Any question? Okay, so if we don't have any question for today, we end there. And then I'm going to send quiz 1 in the group for registered student. If you registered and you have not been added in the group, can you please inbox me so that I add you in the group? Because I'm going to send the quiz after this class. Thank you.